afternoon, Internet. I am Matt Bouyack, and in this video I will show you how to solve the puzzle which has been called Phistomefel's masterpiece, The Ancient Wall. This was the 7th, final, and by far most difficult puzzle in the hybrid Sudoku hunt, which was given as a Christmas gift to patrons of the channel this last December. Now, if you try this puzzle yourself, whether you succeeded or not, I think you'll agree that it is no joke. Personally, I spent about 8 hours on it before I was able to come up with the solution. Though to be fair, much of that time was spent in a state of bafflement, just staring at a mostly empty grid, wondering how I was supposed to make progress. In any case, even explaining the solution as clearly and concisely as I can, I expect that this will not be a short video. So I've divided the solve up into 4 sections, so you have some sense of how the solve will go, what we're focusing on at the moment, and what we'll be focusing on next. So I'll start off in part 1, of course, by explaining the rules. And among other things, it will ask us to divide the cells in the grid into 2 distinct sets. And we'll do that by coloring some cells green and the rest of the cells gray. Beginning the solve proper, we will determine the coloring of the cells in the border of the puzzle. And then in part 2, we'll take a look at row 8, column 1. Yes, that one cell really does deserve a section all its own. In part 3, we'll solve boxes 7, 8, and 9, both the coloring and the Sudoku. And then in part 4, we'll finish off coloring the rest of the grid and any remaining Sudoku. Now that's quite a lot to cover, so let's get started. So let's start by going over the rules. Fortunately, unlike some monstrously difficult Sudoku, this puzzle actually has a pretty concise rule set. Normal Sudoku rules apply, and we're asked to divide the grid into 2 sets of contiguous cells. And as I mentioned in the intro, that just means that we're going to color some cells green, and the rest of the cells we're going to color gray. And I'll note that there are some coloring puzzles which will make a distinction between the 2 colors. It might refer to shaded versus unshaded cells. This puzzle makes no such distinction. The 2 sets are logically equivalent. As far as this term contiguous goes, that just tells us that if we have some green cells down here and some green cells up here, there must be a path moving only up, down, left, and right, and following only cells in the same set, which connects the 2. So now for the tricky part. Digits in a circled cell indicate the number of cells in the corresponding row and column combined that are in the other set. So let's suppose this cell was green. That would mean that cells in the other set were gray. So suppose it sees some gray cells in its row and column, and we'll color the remaining cells also green. So now we can count. This cell sees 1, 2, 3, 4, 5 gray cells in its row and column, and so this must be a 5. And lastly, not necessarily all circles are given. That means this puzzle does not have a so-called negative constraint. To give an example, let's suppose these cells were all green, and we had a single gray cell down here at the bottom. If this center cell had a circle in it, we would know that it would have to be a 1, because it sees exactly 1 gray cell down here at the bottom. But just because there is no circle in the center cell doesn't mean that we can't put a 1 in that cell. It would still be perfectly valid to do so. And those are all the rules. So last chance to try the puzzle yourself. Otherwise, let's get cracking. And as I mentioned in the intro, we're going to begin by trying to determine the color of the cells in the border of the puzzle. And to do so, we're going to steal a trick from a similar puzzle type called yin-yang. This puzzle type also asks you to divide the grid into contiguous regions. And the trick states that either the border will have to be all one color, or there will be precisely two distinct sections of the border, each all one color. And the reason why this has to be the case, let's see what happens if we were to add an extra green section over here on the left. Well, we know that our green region is contiguous, and so there must be some path connecting the green cells on the left over here to the green cells on the right. But now the gray cells up at the top are cut off from the gray cells down at the bottom. And it doesn't help if we try to do it the other way around. We can connect the gray cells to the other gray cells down here, but now the green cells are cut off. And so this arrangement cannot work. We either have precisely two color changes somewhere in the border, or the border is all one color. And so we'll start off by considering that case where the border is all one color. And I think pretty quickly you'll see that there's a problem in this cell here. It's a green cell. It sees only other green cells, and so it should be a 0. And though we can put a 0 into the grid, the software will let us do that. That is not a valid Sudoku digit. And so this arrangement does not work. And so that means that we must have two color changes exactly somewhere in the border. And we can get a hint as to where one of them must be by considering just these cells I've left green in row 1 and column 9. They have exactly the same problem as before. This would have to be a 0. And so we know that specifically one of our color changes is in this section here. Now, to get a hint as to where the other color change must be, let's think about row 9. And what would happen if we tried to make row 9 all one color? I think it isn't too difficult to see that we run into problems with the digit 9. It would be a 9 in a green cell, seeing only other green cells in its row, and it could see at most 8 gray cells in the column. So there would be no way to satisfy 9 in this row, no matter where you put it. And so there must also be a color change somewhere down in this row. And so we've accounted for both of our color changes. We have one somewhere in here, and we have one somewhere down here. And so there must be no color changes in column 1, and we can make them all green. Now I'll note that the choice of green is entirely arbitrary. It would be just as valid to use gray as your first color instead. I just chose green because I wanted green. Now the eagle-eyed among you might wonder if I've made a logical mistake here. I mentioned that we have to have a color change somewhere in these cells and somewhere in these cells. But you might wonder, is it possible to put the color change down in the corner and satisfy both sections, thereby freeing up a color change to put in column 1? But you can't actually have a color change in a single cell. There's no way to make half of this cell green and half of this cell gray. Any color change you put in the corner will actually be properly in the column or be properly in the row. And so our logic is free from any literal corner cases that might cause us issue. Next, let's consider this cell up here. We know that there has to be at least one gray cell somewhere in this row in order to satisfy this one. But that means there has to be a color change somewhere in this row. We also know that there's a color change somewhere down in this row. And so again, that accounts for both of our color changes, and this column must be all one color. Which color is it? Well, let's start in the top left here. And as we traverse row 1, at some point we're going to encounter a color change and switch from green cells to gray cells. So by the time we get to this cell here, this cell must be gray. Or equivalently, we could start down in this cell and traverse row 9 and at some point encounter a color change and switch from green cells to gray cells again. And so this would be gray, thinking about it from row 9. And so in either case, this column is all gray. This cell here is satisfied, that is, it sees one gray cell, so the remainder of the row must be green. So now we only need to figure out the coloring for these cells down in row 9. And we'll start by thinking about this cell here. What would happen if we tried to make this cell green? Well, that would give us our one color change for the row, so the rest of the row would have to be green also. But now we have a problem because these two cells are both gray, they both see no green cells in their column, and they both see 8 green cells in the row. And so they would have to both be 8, which breaks the puzzle. That means that this cell cannot be green, it must be gray. And now we'll take a look at where 1 might go in this row. Obviously, it can't go in column 1. We already have a 1 there. And if we try to put a 1 in any of these cells, for example here, we already see 2 green cells and 2 gray cells. And so no matter where we put 1 in any of these cells, and no matter how we color it, it wouldn't be valid. What if we try to put a 1 in this cell? Well, again, it's a gray cell. It sees 2 green cells, so that would also not be valid. The only place we can put 1 in this row is in the bottom right corner. That cell is now satisfied. It sees its 1 green cell, and so the rest of these cells must all be gray, and that finishes our coloring of the border. So the goal of this section is going to be to determine the value in this cell right here. But before we get to that, let's tackle a few easy digits. We'll notice that these two cells both see exactly 8 cells of the opposite color in their respective rows, and so they must both be 8. Next, we can consider where we might put 9 in column 1 or column 9. And what we'll find is if we try to put 9 in a cell with a circle, we won't be able to allocate enough cells of the opposite color to satisfy that 9. You see, there are only 8 gray cells available here at a maximum. And so that means that 9 must go in the only cell in this column without a circle, and must go in the only cell in this column without a circle. And now we're ready to begin our siege on row 8, column 1. But rather than just diving into a bunch of arithmetic and leaving you lost and confused, I want to give you an overview of how this trick is going to work. Let's suppose that somehow we could determine the number of green cells in this red rectangle here. And let's also suppose that somehow we could determine the number of green cells in this green rectangle here. It would actually be possible, knowing those two numbers, to determine the value of this cell here. If you haven't seen this trick before, perhaps pause the video and see if you can work that out for yourself. For those of you who managed to do it, congratulations. And what we'll see is that if we start with the number of green cells in the green rectangle, and we then subtract these 7 cells at the top, and then add these 6 cells on the left, and then subtract all of the red rectangle, that leaves us with the number of green cells in this strip down here. We can add row 8, column 1 itself to get 1 additional green cell in the row, giving us the total number of green cells in that row. We then subtract that number from 9 to get the number of gray cells in that row, and that corresponds exactly to the value of row 8, column 1. Which might seem very clever, but so far I've only told you how to calculate something we don't know in terms of 2 other things we also don't know. So how might we go about working out the number of green cells, for example, in the red rectangle here? Well, the trick is to understand what it is these cells in column 9 are telling us. There aren't any green cells in this column, so each of these cells is telling us exactly how many green cells are in the row. That means that if we add up the values of these 6 cells, we're going to get the total number of green cells in the red rectangle. But how do we determine that sum? We don't even know what the contents of these cells are. And the answer, of course, is the secret. Now, the secret is something that Simon only tells his favorite people, but you're all in luck because I happen to be one of them. Now, he told me not to share this with too many people, but I suspect if you're watching this video, you might also be one of his favorite people. So the secret tells us that any complete row or column or box of a sudoku, if we add up all the digits, we're going to get the number 45. And so we know that the sum of all the digits in this column is 45. We can subtract 18 to get that the sum of these cells is 27. And that's exactly the number of green cells in this red rectangle. So we'll make a little note to ourselves up in the corner that there are 27 green cells in the red rectangle. And now let's see if we can do a similar trick for the green rectangle. And you might think that we can just add up these cells down here and get a similar result. But we have to be careful because these cells are not telling us the number of green cells in the column because they also see row 9, column 1. They're actually telling us the number of green cells in their respective columns plus 1. So we have to be sure to subtract 1 from each of these cells after we calculate their sum. And again, we can start with a secret. If we add up all these cells, we're going to get 45. We can subtract 9 to get 36. And then we can subtract 7 more, 1 for each of these cells, to get 29 total green cells in the green rectangle. Now, as I summarized before, we're going to start with this value. We're going to subtract 7 for these top cells to get 22. We're going to add 6 for these cells on the left to get 28. We'll then subtract 27 to get just a single green cell in this strip of cells down here. We're going to add 1 more to account for row 8, column 1. That gives us 2 green cells for the row, which means we have exactly 7 gray cells for the row. How cool is that? Welcome to part 3. In this section, we're going to try to tackle boxes 7, 8, and 9. But before we're ready to do that, we need to make some critical observations about how the circles in column 1 relate to the circles in column 9, and how the circles in row 1 relate to the circles in row 9. In the previous section, I had mentioned that the circles in column 9 are counting the number of green cells in their respective rows. And as you might expect, the green cells in column 1 are counting the number of gray cells in their respective rows. But that means if we take 2 opposing circles in columns 1 and 9 and consider their sum, that would just be the sum of the number of green cells in that row and the number of gray cells in that row. And that's just all the cells, or 9. And so if we add up any opposing pair of circles in columns 1 and 9, we're going to get 9 as the sum. And you might expect there to be a similar relationship between the circles in row 1 and the opposing circles in row 9. And you would be correct, but it's not quite as simple as that. In particular, you'll recall me mentioning again in the previous section that these circles down here are not counting the number of green cells in their respective columns. They're counting that number plus 1. Similarly, the green circles up here in row 1 are not counting the number of gray cells in their respective columns. They're counting the number of gray cells plus 1 because they see this extra gray cell up here in the top right corner. That means if we take 2 opposing circles in rows 1 and 9 and we add them together, we get the number of green cells in the column plus 1 plus the number of gray cells in the column plus 1, which is going to give us all the cells in the column plus 2, or 11. And so this is the so-called rule of 11, that 2 opposing circles in rows 1 and 9 are going to add to 11. And now we're ready to consider what would happen if we tried putting a 2 in one of these cells here. And by the rule of 9 that we just worked out a moment ago, we know that we would have to put a 7 in one of these cells here. And that breaks the puzzle because we already have a 7 in that column. That means that none of these cells can be a 2. We have to put a 2 down here. Now, by Sudoku, we must have a 9 down at the bottom of box 8. And let's consider what would happen if we put 9 into a specific cell, say this one here. Well, we would have to finish coloring that column with all green cells in order for it to reach its total of 9 green cells. This cell would see its 2 green cells in the row, and so the rest of those cells would have to be gray. And this cell sees only a single gray cell in the row thus far. So in order to reach a total of 7 gray cells, the rest of these would also have to be gray. Keep in mind, this is purely for illustrative purposes. So we have to be careful that any logic that we do based on this illustration is going to still be true if, for example, the 9 were here with the column of green cells there, or if the 9 were there with the column of green cells over here. But there are some observations we can make. And the first is that wherever we put the 9, there must be an 8 in the circle above it. And that's because that circle will be green, and it will see 7 gray cells in the row and 1 at the bottom of the column for a total of 8. The other observation that we can make is that these cells will always be gray. No matter where we position the 9, it only will affect the coloring of these cells, not the coloring of the cells in boxes 7 and 9. And the third observation is, I think, much more difficult to see, but is probably the most crucial. And we can find it by considering the relationship of these two cells here. They're both gray. They see the same number of green cells in the column, but this cell is going to see 2 green cells in the row, and this cell is going to see only 1 green cell in the row. And so this cell must be 1 greater than this cell. And that logic is going to hold for this pair of cells, and 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 this pair of cells. One point of caution, we don't actually know where the 9 goes, but the other 2 pairs that do not involve the 9 will follow this rule. And so now, keeping those 3 observations in mind, let's return to what we know to be true. And we can immediately pencil mark an 8 into one of these cells because we know that 8 must go above the 9. Now, when I was solving this puzzle the first time for myself, at this point I got stuck for quite a while and spent a lot of time pencil marking different possibilities into these cells and slowly narrowing down the different combinations in a very tedious and error-prone way. And I think it's a bit difficult to find the right question to ask from this point. But it turns out that the right question is, what happens if we put a 5 into this cell here? Now, 5 doesn't seem to be particularly restricted, but let's see what happens. Well, by the rule of consecutive circles that we just worked out, this has to be a 6. But by the rule of 11 that we worked out earlier, this also has to be a 6. And so this cannot be a 5. Now, the rule of consecutive circles is going to hold no matter where we put 5 in this row. So that gives us no escape. But the rule of 11 does not hold in these cells here. And so we must have to put 5 into one of those 2 cells down here. So now we know that none of these cells can be a 5 or an 8. Neither can this cell. And so by the rule of 11, none of these cells can be a 3 or a 6. And that's because if any of these were a 3 or a 6, we would have a 5 or an 8 down here. That means we have a 3-6 pair up in these cells. Similarly, we can't put an 8 into any of these cells. And so by the rule of 11, we can't put a 3 into any of these cells. And that gives us a 3-5 pair in these cells here. And by the rule of consecutive circles, we have a 4-6 pair in these cells. Next, we're going to consider where 7 goes in this row. And in particular, we're going to see what happens if we try to put 7 into one of these 2 cells here in box 8. Well, it would form a 7-9 pair. And we'll recall that 9 has to have the 8 in the circle immediately above it. But 7 must also have an 8 immediately above it. And so we would end up with double 8 in box 8, which, though perhaps appropriate, is not legal by the rules of Sudoku. And so we cannot put 7 into box 8 here. We have to put 7 over into box 9. That gives us an 8 in this circle here by the rule of consecutive circles, and an 8 here with the 9 below it here. Recall the 9 has to go under the 8. That allows us to color these cells green and these cells gray by the logic that we looked at previously. Okay, now considering box 9, we have 3, 4, 5, and 6 remaining. And this 4, 6 pair gives us a 3 or a 5 in this cell. Now we have a 3, 5 pair, leaving just 4 or 6 in this cell. And this 4, 6 pair now resolves 6 and 3, 3 and 5 and 3. The 6 gives us 6 and 4 and 4. Now let's think about where 2 goes in this row down here. We're running out of space, but wherever it goes, it has to have a 3 above it, keep in mind. That is, one of these cells has to be a 3. But this one sees a 3 in the row, and this one sees a 3 in the box. And so this must be a 3 with a 2 under it here. Now by Sudoku, we have a 4 in this cell with a 5 above it. And this cell must be a 6 with a 7 above it. The 6 resolves this box with a 6 and a 1. We can finish off this row with a 2 and place a 1, 5 pair to finish off boxes 7, 8, and 9. Welcome to part 4. We're on the home stretch now. We just have to figure out how to color the rest of the grid and solve the rest of the Sudoku. Shouldn't be any problem. So we'll start off by applying the rule of 11 that we proved in the last section. And recall that that just says that if we have 2 circles across from each other in rows 1 and 9, that they must add up to 11. And so we can just write in 9 here, 7, 2, 5, and 4 in row 1. Now we can do some simple coloring. This cell here sees 3 green cells already, so the rest of this column must be gray. This 8 sees only 3 green cells, and so in order to reach a total of 8, all the rest of these cells must be green. And now we get to one of my favorite tricks of the puzzle. Though really there are so many cool tricks, it would be hard to choose just one. And we find this trick by considering where 7 might go in this column. If we try putting a 7, say in some middling position like here, it sees 3 green cells in the row, but must see a total of 7. And so all the rest of these cells must also be green, if 7 were in this position. But now you'll see that we've isolated these cells from the rest of the grid. And if we tried to put some gray cells in here, they would be separated from the other gray cells. And you'll recall that our 2 sets must be contiguous. And so all these cells would also have to be green. And that breaks this cell down here. It's supposed to see exactly 3 green cells, and instead it sees 5. And the only way that we can satisfy that cell is to push the 7 all the way up to the top of column 9. We still color the rest of row 2 green for the same reasons, but now we have the same number of green cells visible to this 3. That means we must color the rest of this column gray, And we can use the rule of 9 to write a 2 into this cell. You'll recall that similar to the rule of 11, the rule of 9 just says that opposite circles in columns 1 and 9 must add to 9. And now we can use a trick similar to the one that we used to narrow down the location of 5 in row 9 here. But instead we're going to consider these two cells in row 5. They're both green. They see the same number of gray cells in their row, but this one sees no gray cells in the column, while this one sees 3 gray cells. And so this cell must be exactly 3 greater than this cell. And we can write in the possibilities for this cell as 3, 4, 5, and 6, just looking at the digits remaining in this column. If we add 3 to each of these possibilities, we discover that these must be 6, 7, 8, or 9. But we already have a 7 and an 8 in that column, and so that rules out those possibilities. Then subtracting 3 from those, we rule out 4 and 5 from this cell. Now we can see what happens if we try to put a 3 into this cell here. We know that this cell would have to be 3 greater, so it would have to be a 6. But by the rule of 9, this cell would also have to be a 6. And so this cell cannot be a 3, it's a 6. That puts a 9 in here and a 3 in here. Now we can do a very similar trick looking at these two cells here. And we can determine their relationship using the exact same kind of logic. They're both gray, they're in the same row, they see the same number of green cells. This one sees no green cells in the column, this one sees exactly 1, and so this cell is 1 greater than that one. Just looking at the possible values in the column, this must be 4, 5, or 6. That means this must be 5, 6, or 7, but the 6 here rules out a 6, which rules out a 5 back in this cell. Now we can see what happens if we try to put a 4 into this cell. We know that this cell must be 1 greater than that one, so it would have to be a 5. But again, by the rule of 9, this one would also have to be a 5, breaking the puzzle. And so this cell is not a 4, this cell is a 6, this cell is a 7. By the rule of 9, we can put a 3 into this cell. By sudoku, we can put a 4 into this cell, finish the column, apply the rule of 9, and we finish that column as well. And we're starting to see the light at the end of the tunnel. We see that this cell here is satisfied. It sees exactly 3 gray cells in the row, and so the rest of these cells must be green. We see that this cell now sees its 4 green cells, so the rest of these cells must be gray. We see that this cell sees 4 gray cells in the row, so these must be green. This cell now sees 5 green cells, and so these must be gray. Our 5 is satisfied, seeing 5 gray cells, so this must be green. And our 6 needs 1 more gray cell, and so this cell is gray. And now we can just do some basic counting to determine the value of our remaining circles here. This cell here sees 3 gray cells, so that's a 3. This green cell here sees 1, 2, 3, 4, 5, 6, 7, and 8 gray cells. This green cell here sees 1, 2, 3, 4, 5, 6, 7, 8, 9 gray cells. And this cell here sees 1, 2, 3, 4, 5, 6, 7 green cells. And so now we have only the Sudoku remaining. We can start by putting a 2 into this cell here. We can look at 3s and put 3s into this cell here and this cell here. We can take a look at 4s and put 4s into this cell here, here, and here. We can take a look at 6s and see that we have a 6 here, and here, and here. Looking at 7s, we have a 7 here and a 7 here. Looking at 9s, it looks like we have a 9 in this cell, and a 9 in this cell, and a 9 in this cell. Now if we look at row 6, we see that 2 is limited to just one location right here. We can see that 1 must go into these 2 cells to finish their respective boxes. We put a 1 in this cell, a 1 in this cell, and in this cell. That resolves our 1, 5 pair. So we have a 5 down in here, a 5 here, a 5 here, and a 5 here. We can finish off our 2s here and here. And I believe we should have only 8s remaining in those cells. And that's how to solve the ancient wall by Phistomefel. Thanks first to Phistomefel for creating this puzzle in the first place, along with the rest of the hybrid Sudoku hunt. For those of you who haven't tried those puzzles yet, they're still up on Patreon. I would strongly encourage it. Every puzzle in the hunt is absolutely brilliant. Thank you so much for watching, and I hope to see you again sometime.